These are the equilibrium equations that we get from flying a stable aircraft. And the CM0L means zero lift. So that's got a bar on it. Couldn't draw a bar. So that's the same thing as having the bar on it. And if you slow down, then you'll move to the right of that curve at a higher CL. If you speed up, you'll move to the left, showing as the green line. Moving to the right, slowing down, is pulling back on the stick. So if you pull back on the stick, the elevator will go negative by our convention, because you will dump lift at the tail, and when you dump lift at the tail, the aircraft will rotate up and climb at a higher CL. So if you go fast, the opposite happens. So the green line is a push forward, and you'll trim at a higher speed, and the red line is a slow, you'll trim at a lower speed. You can find your C sub L using the equation wing loading over dynamic pressure, and there's your formulas for those. I guess I'm just repeating what I've done before. Static margin increases, and if you move the CG aft, it will decrease. Now this is different than pulling back on the stick. When we pulled back on the stick, the whole blue curve went up or down, right? It went up and down by a constant, by the constant that's in the stability equation for lift. Now we've changed the slope. We've either increased the slope negatively, which means I increased the static margin positively, or I've decreased the slope negatively, which means I've decreased the static margin positively. And you can see as I decrease the static margin, then I'm going to go into trim at a higher C sub L at the same elevator deflection. This elevator deflection hasn't changed, so whatever it is for the blue line, it's the same for the red and for the green. So I can put myself in trim at farther aft, as I move the center of gravity aft towards the CG, or the center of gravity towards the aerodynamic center. So what keeps me from going to the right, just keep going at higher and higher and higher CL? What keeps me from doing that forever? The C sub L's of 3, 4, 5. Why can't I do that? What will happen to the airplane if I keep moving my CG aft? I'll stall, right? Once I get to the stall angle of attack. So it's always nice to plot the stall angle of attack on these curves, remembering our fundamental formula, the fundamental equation of longitudinal static stability as shown there. So if I want to plot a constant alpha curve, then I normally pick 2 points. I'll pick 2 points, 2 elevated deflections, like so. And from those 2 points, I'll draw a line, and that black line on the top curve then is a constant alpha curve on the line. So all I have to do is go down here and pick the stall line and repeat that, and that will give me my aft limit for the stall. You have it? So you want to plot that stall line on your curve. Here's the catcher. Here's the head fake for the test, okay? Here's the head fake for the test. That stall line you plotted, it's only good at the CG location that you chose. Think about it. When I pick these 2 points here, yes? Do those 2 points depend on the slope of that curve? In other words, if I change the slope of the curve, am I not going to move the points? Certainly. So as I move the static margin up or aft or forward, these points are going to change. What does that mean with my stall line? My stall line will move right and left on the CMCL curve. I just determined the difference between an A+ and an A- in the class. For those of you who remember that, right? As I change the stall line slope up and down, the alpha stall curve will move to the right and to the left. Okay? So you have to remember that. Now, why would that be the case? Well, if I move the center of gravity forward, I download the tail more, yes? I download the tail more. I still have to be in equilibrium. So if I'm still in equilibrium with the more downloaded tail, where's that lift going to come from? Got to come from alpha, yes? So I'm going to hit the angle of attack for stall sooner if I download the tail, because the angle of attack has to be making up for the lost lift at the tail. Yes? So as you move the center of gravity forward, you'd expect the aircraft is going to stall at a lower CL and stall it up. The opposite happens when I move the CGF. I'm going to start uploading the tail, or I remove the download on the tail. Now I'm going to stall actually at the wing angle of attack when I remove it. So at neutral stability, the wing will stall when it's supposed to stall. But whenever I have a load on the tail, I'm going to change that angle of attack. So therefore, that moves the angle of attack curve. CL0. CL0, there's the lift curve. I want the lift at 0 angle of attack and 0 elevated deflection. It's going to be right there. Okay. Make sure you don't have an elevated deflection when you pick this curve. So that's the value right there, CL0. CL alpha. Delta CL over delta alpha. Lift curve slope. Either one of them will do. Yes? Positive number. Turn your head 90 degrees and you see a positive number. CL delta E. CL delta E. That's the lift due to elevated deflection. So we know a positive elevated deflection. Trailing edge down, I'm going to have a positive number. So CL delta E will be any two curves. This 0.2 minus this 0.1 will give me two lifts and positive number. 0 minus a minus 5 will give me a positive number. CL delta E will be somewhere around 2 pi, between pi and 2 pi. Okay, moment curve. CM0. CM0 means alpha 0 and delta E is 0. So alpha has to be 0, so I have to be over here, and delta E has to be 0. So that gives me this point. This point has to be mapped up onto the top curve. So I take that point, I map it up to the delta equals 0 curve up here, and I come across and I reach CM0, like so. That's CM0. Not CM0 lift. That's the pseudo-derivative. Okay? CM0 lift is a function of CM0. And if you look at the formula, it depends on the slope, which obviously makes sense from looking at it. CM alpha. Wow, that's too hard. So let's go to CM delta E. CM delta E, that's delta CM over delta delta E. So I can take any 2 points here, but if I take the points vertically, take that CM minus that CM, that delta E minus that delta E in the denominator, I will get the wrong answer. Because I don't have constant alpha, and the partial derivative, CM delta E, means I'm holding the other derivatives constant, or the other variables constant. So I have to be on the black line, or some alpha line. I have to be on a constant line. Okay? So I take the 2 points, this one across there, and this one over here, the 2 delta E's, and that will give me a negative number. Do you see how much bigger this can be? Look at that. If I take this number, this second point is going to be the same for CM. They're both going to be that number. But the vertical line will give me this number, and the correct answer will give me this number, almost double, right? So you'll be off by 100% if you, pretty easy to spot the wrong answer, okay? Okay, so the Taylor expansion is only a function of alpha and delta E. All right, now the difference between A and A minus. CM alpha is delta CM over delta alpha. Well, I got delta CM okay, but where am I going to get delta alpha from? Because I only have one alpha curve. I need to draw another alpha curve. So if I drew the stall curve, or maybe the landing curve, either one, I would have another curve like so. So I'd have this would be the new alpha curve. That's the old alpha curve. Now I can pick 2 points. Now I can pick 2 points at the same elevated deflection, because I'm holding elevated deflection constant in the partial derivative. Yes? That's the definition of CM alpha, means that the elevated deflection is constant. So I can pick either the red line or the blue line once I pick my 2 alphas, either one. Take the 2 points. I'll take this point and this point. Take the difference in the numerator between the 2 C sub m's. And then in the denominator, I take the difference between the 2 alphas. The alpha for the black line and the alpha for my point. And that will give me the correct value for CM alpha. So that's very important, right? I can move my CG forward because that's the fastest I can go for landing. That's my min C sub L. I can't go any faster than that. I'll run off the runway at the weight I'm at. So, and what CG limit is allowed for that? Well, going forward, my CG limit would be the angle between the 0 line and that. That angle would be the percent center of gravity. I can move forward to give me that C sub L. How about aft? Well, aft, I can move aft from the zero line to that angle, whatever that angle is in radians, is the percent aft I can go. The percent aft would go this much aft from the zero line, and that would give me C sub L for stall over here moving aft. So my C sub L, that's greatly exaggerated. Usually this side of the triangle is like that. So I have from C sub L from here to here, I can control by moving my center of gravity. Because you realize that the tail is actually worthless, right? I mean, it's not carrying any fuel, it's not carrying any people, there's no luggage in there, it's just worthless weight. So you want to make you don't want to make the tail to be any bigger than it needs to be to give your aircraft stability and control, because it's worthless weight back there. And that's why you see flying wings are so efficient when they're built right. Right? The flying wing is very efficient because it doesn't have any excess useless weight. Remember, your primary design for your mission only depends on the wing that you pick, not the tail. The tail is just an appendage that you're trying to minimize. Look, all right, so one more time, looking through, if you want to compute the slopes, these stability derivatives, use delta CM, delta CL, and pick 2 points. And what's the key between a high grade and a medium grade? The key is remembering that these stability derivatives are partial derivatives. So if I'm taking one of them, I have to hold the variables constant. I have to find the constant lines on the charts before I compute those. Okay. Here are your design equations. And let's go through these one at a time. All I want you to do is to understand what these design equations are for now. And tomorrow we'll go into some depth what they are. Here's your stability for the moment equations. So for this one, we've taken off the tail. So I just have the wing and the body, and the wing body hooked up. That's nice because almost all wings have an aerodynamic center of 25%, quarter chord. Roscom has a beautiful, almost always 0.25. So that becomes something that's, for all wings as we know them, is pretty much the fixed design parameter. So this A to H means for horizontal tail. And what this means is that the dynamic pressure at the horizontal tail is different than the dynamic pressure that the wing sees, right? Because of downwash. So the ratio of those dynamic pressures, the ratio of the head pressure here, and the head, if I had a pitot system on the tail and at the wing and took the ratio, I'd get eta. Right? And so normally we use around 0.9. This is called the tail volume coefficient, TVC. And it's got its own formula down here. It's got its own formula. So I'm going to put that in your pocket right for now. This tail volume coefficient, that's a primary design parameter that we're going to be working with. You want to minimize that for your design. Right? You want to make the tail as small as possible. So this is the angle of attack of slope of the horizontal stabilizer. The H means horizontal stab. So that's your lift curve slope of the horizontal stabilizer. And this DED alpha is downwash. It's the rate of change of downwash as angle changes, as the alpha changes. So your downwash angle looks like if you can imagine it's going through water, and you can see the water, or a wind tunnel, a water tunnel. Going through a water tunnel, you see the water would go over it like that, and then you'd have a downwash at the tail. That downwash will change with alpha. The more alpha you get, the more downwash you get. Pretty much obvious from physics, yes? So the rate of change of that downwash with alpha is going to have an effect on stability. It's going to have an effect on the moment due to stability, because you're going to be losing your angle of attack at the tail. The angle of attack at the tail, alpha H, this angle of attack is reduced by the downwash angle. Especially important for big airplanes, for obvious reasons, with lots of downwash. This is static margin. Now you're going to use this for static margin, and this I would say is the primary design equation that's important, is the static margin equations. And the last one is tail volume coefficient. Let me just say a few words about that. It's the ratio of the area of the horizontal tail. It's the ratio of the area of the tail to the area of the wing. So that's the wetted area. The tail volume coefficient goes up as you make the horizontal tail bigger. This is the moment arm. That's from your datum plane to the horizontal aerodynamic center. So wherever the horizontal tail has its aerodynamic center here, from wherever my datum is, that's going to be a long moment arm. And that minus the CG position is going to be the moment arm that the lift acts at the tail. Make the horizontal tail small by itself, or you can move the horizontal tail closer to the center of gravity. Right? You can push the tail in. So these are the equations we're going to use tomorrow.